Hello and welcome once again for another ES340 video. And learning from last time, I am actually going to make this short enough that I split it into a couple of videos, so there is going to be a second part, so I don't overrun time too much. Okay, so this time we're switching to a new topic. It's Exergy, but it's going to follow at this point. I think you should start to see a pattern. It's going to follow the same pattern that we've done before. So first, we started off with the first law of thermodynamics, and then we discussed energy, energy conservation in closed systems, the energy balance equation, then the energy rate balance equation for open systems for control volumes. Then we moved on to entropy and did the same kind of thing. And now Exergy, once again, we're going to go through the same kind of flow, and we'll see how that goes. So what is Exergy is obviously a good question. So for the first pass, we're gonna think of Exergy as being the potential useful energy. Okay, and I'll give a full definition later in a moment later, but for now, just think of it as the potential useful energy. So you could imagine, for instance, if I say have a piston, right? And I have injected some fuel into the piston. So now I'm going to, for the time being, I'm going to model the piston as just a closed system. I'm going to say we've sealed it off. We can no longer inject fuel into it, but that it has some fuel inside already, and we can obviously I'll take the whole piston plus, say, the spark plug to be my system. Okay, so I take the spark plug, I ignite it. I ignite the fuel mixture with a spark. It burns, obviously. It produces some kind of upward pressure on the piston, pushing it up and whatnot. And that's it. Now there's no opportunity now anymore for any other kind of, obviously I can't put fuel back into it or anything like that. So in this case, notice that when I had the mixture, and we're going to assume, of course, that none of the gas could escape because it's a closed system, right? We're going to assume that there wasn't any ability for any mass to be transferred in or out of the system or anything like that. So out of the piston plus spark plug, right? That's our system. And the question is then, when I went through this process, at what point in the process was I able to extract more work, right? And that's kind of going to be the key to thinking about Exergy, because it's the potential usefulness of the energy that we're going to really care about. That's what the Exergy is, right? So at the beginning of the process, obviously, I had this mixture, this mixture of gas inside there that could be ignited, and we could extract work by raising the piston, right? We were able to raise the piston by combusting that gas. But once the gas has been combusted, notice that since it's a closed system, we didn't lose any of the mass. We technically didn't lose any energy in this system, right? There was no transfer of energy out of the system. We just did work by raising the piston, right? So there was no extraction of work or anything like that. But guess what? The first state was very useful in terms of energy to be extracted for work. Now that it's been combusted, and we can't kind of recombust that gas mixture now, right? It's been somehow utilized. The fuel has been used. Okay, so in that case, then the second state is obviously not as useful to us anymore. And so we want to kind of quantify that, and that is what Exergy is. Exergy quantifies the usefulness. How much work could I extract from this system at any given time? It might have some internal energy, right? The same amount of internal energy in both cases, but in one case I have more energy that could be extracted as work. Okay, so the things to note about Exergy, it is a property, just like those other things that we have discussed before. We discussed energy, we discussed, obviously, temperature, pressure. We discussed we've discussed enthalpy. Now we also have entropy. So it's a property just like those things: energy, entropy, and now Exergy are going to be things that we deal with equations for generally. Okay, it's not conserved. So in this case, it's kind of similar to entropy, right? We know that energy is conserved, at least when we're dealing with non-relativistic speeds and things like that, where you can't have mass changing back and forth between energy, which is the systems that we've been studying. So the energy is conserved, mass is conserved, right? But entropy, as you should remember from the last chapter, was not conserved. And in fact, it can increase, right? It can be created. Entropy can be created and obviously transferred between systems, but it can be created. Now, Exergy is the flip of that. It actually can be destroyed, and it can be destroyed by irreversibilities. So before, entropy we create with irreversibilities. Now, Exergy is destroyed by irreversibilities. And just like entropy can be transferred back and forth. Okay, so Exergy takes that role of being able to be transferred between systems. So the way, as I kind of already hinted at this point in the initial example that I gave, really the Exergy is kind of measuring that potential for work that could be done, right? That's going to be the key thing. We really want to know how much work could be done. So we can think of it as like, if I take now let's do another example with say a cup of coffee. Okay, so if I have this hot cup of coffee, it's obviously warmer than the atmosphere, which means that heat energy is going to be transferred from the hot cup of coffee to the to its surroundings, to its environment, right, to the atmosphere. So that hot cup of coffee is transferring some energy to the atmosphere, and because it's transferring some heat energy there, that means that if I were to attach some cycle to it somehow, in fact, that's exactly what happens with a Stirling engine, and I suggest that you go and take a look at a Stirling engine at some point, say a YouTube video or something. The Stirling engine can be set on top of that hot cup of coffee, and it can actually do some work, right? It has like something that's like a piston that goes up and down. I think it is a piston actually, but goes up and down as a result of the heat energy. So now I attach some kind of cycle to that hot cup of coffee, and I'm able to extract work, something useful, right? But as the cup of coffee cools off towards the environment, as it equilibrates with the environment, I can extract less and less work, right? So if it starts off at some temperature, there is at some temperature, say much higher than the atmosphere, it has the ability to do more work than if it starts off very close to the temperature of the environment. Okay, and actually you can do this with cold things as well. It's just that the flow of heat goes in the other direction, right? So the hot cup of coffee, I'm going to have heat coming from the coffee out and then, going into the cycle. If it was, say, some ice, a block of ice, I would actually have heat flowing from the environment into the ice, right? So the flow goes in the opposite direction. But if I attach a cycle to that, I can still get useful work out of it, okay? So I can still develop work by doing that. And it's a similar kind of idea. As I get closer and closer to equilibrating with the environment, I'm able to extract less and less useful work. Your book likes to denote the environment in this case with an O, or maybe that's a 0. I can't really tell. I think it's an O. But basically TO and PO, these are, we can think of them as two things. We're going to call them two things, okay? One is that they are the environmental temperature and pressure, TO and PO, which is true. That's going to be, the environment, because obviously a system, unless it's isolated, has to interact with its environment. Excuse me. And typically the values for those will be taken as 25 degrees Celsius, an average atmospheric temperature, and the pressure will be taken to be 1 atmosphere. Okay, that's typical. Obviously, if you're say high on top of a mountain or boring into earth or something like that, you're going to get different values for those things. And maybe if it's winter, you get a different temperature, those kinds of things. But that's what we'll take these to be under typical circumstances. Okay, and then that leads me directly into this discussion about what's called the dead state. Okay, so the dead state is when the system that's in question, the thing, for my starting example was that hot cup of coffee. When that has equilibrated with the environment, that is called the dead state. So it takes on the temperature, the TO, and the pressure, the PO, of the environment at the dead state. Okay, so we're thinking of the system reaching equilibrium with its environment, and that is when it is at its dead state. Okay. So the last thing I'm going to do for this video, and we'll have a clicker question here, is actually give the definition of exergy. I promised I was going to do that, so let's give that definition. Exergy is the maximum theoretical work obtainable from, and I'm going to call it overall, this is how your book uses the language, overall system consisting of both a system and its environment as the system comes to equilibrium. Okay, so obviously the amount of exergy that you could have changes in time, right? Because as I'm cooling off, if at say time 0, I started off, I heated up that cup of coffee and it's 100 degrees Celsius, right? It's boiling. It's going to have a different amount of exergy than at some time later. Let's say 1,000 seconds later, it's reached 50 degrees Celsius. I don't know that that would be true. It's probably going to be much faster than that, but you get the idea. It's reached 50 Celsius at some time later. At that time, it has a different amount of exergy, right? Because eventually, at some time later, far enough into the future, it's reached 25 degrees Celsius, which is what we're taking to be a typical dead state value, okay? So at that point, obviously, the amount of work that could be done is zero, and that will hopefully help us think about the very last thing, which is the clicker question that I have for you. So my question is, at the dead state, the exergy can be taken to be zero, obviously, from that previous discussion that we just had. What must be true of the exergy of a system if it is not at the dead state? The exergy is greater than zero, less than zero, greater than sigma, which is the irreversibilities, right? The strength of the irreversibilities, or it can take on any real value. That's all I have for this video. I have a second video coming up soon, so come see it.